I think the brief intro for me would have simply been, and now for something completely different, because certainly looking at the talk summaries and abstracts, mine is very different than anything else this morning, but it's what we do. And we're not in there in the nitty gritty of how you do your work. We are very much a tool for people doing fundamental things with the design of installations, and sometimes custom work, sometimes just broad product design. So I thought the most useful thing I can talk about is just the one area that I advise people on the most in my day-to-day work, and that's how to make more efficient use of your software. So that's very broad, very specifically our software, next to any similar software, but software in general, you can make much better use of by really leveraging off of a few expert users to automate in particular. So what our software is used for is to address issues such as what you see here, sizes and shapes of parts, what happens when you turn voltages on and off, use different materials and hence different material properties, tolerance testing, like you've got things like your press boards and foils and things in your transformer, what happens when things are a bit misaligned. You know, you can play around with all kinds of things on the computer and get answers that should be useful, covering a variety of technical problems that can come up with an actual proposed installation. And so you may notice my slide is very dense in text. I'm not necessarily going to read everything on it. I did that deliberately so that anybody wanting to review it won't have to actually listen to me again. The presentation is self-contained. You can take the PDF or PowerPoint and go through it to review some of the things that I've talked about. But as I said before, down at the bottom here, really leverage off a few trained people rather than relying on everybody being able to do everything. When you automate things. Did I just draw accidentally something on the screen? No, there's a red line across my screen.
There's an annotation tool that
okay.
maybe you activated.
It's not activated on my end. It's not showing it.
Well, keep going. It's all right.
Yeah. And anyways, I'm not sure how that ended up there. I'm not a Zoomer. I do a lot of other presentations, but Zoom is actually relatively new to me. So yeah, the thing about automating is that you get around all the tedium, but you can also get things done an awful lot faster when you automate. And there's two broad categories of automation for software. One is to do things in a parametric fashion, and the other thing is to do things in a scripting fashion. Scripting is much harder, much more upfront work, but you can do far more powerful things with it, where parametrics let you take something that looks like a huge job and maybe just do a little bit of setup and then let the computer take care of all the details for you. So yeah, here's some examples of some of the things that get done with our software in particular that are relevant to the transformer industry. People are looking at things like field values around different aspects of their installations, whether it's the power lines coming out or the transformers inside, and that could be electric fields, magnetic fields, it could be heating, any kind of fields that may be present could be simulated with software of our type. So my purpose in what I'm going to show here isn't to talk about active topics of the design. That's what our users do. That's not what I do. What I do is I help people make decisions when they say, I'm trying to figure out this about something, again, to do with heating, to do with the inductances, the fields, and so on. I'm trying to figure out this. How do I best do that? And I don't even know a lot of the times how proprietary, how company specific things I'm being told are. We do non-disclosures and all that, but I just avoid talking to people about anything other than what they just asked me about, in order to not accidentally divulge things. The most useful thing I can do is to talk in very general terms. So I'm going to talk about a few types of analysis that we can readily automate, and what kind of trade-offs there are when you do that automation. So here's a sample. It's a very trivial engineering drawing. As you can see, just a cross-section of a transformer, primary coil, secondary coil, but you can get a lot of information out of this related to field strengths, how the flux links between the coils, and so on. We can get inductances, power distributions, transient responses, how your voltages step up and down. We can get many kinds of performance issues out of a trivial model like this. So just looking here, does this panel show up in my screen? It's kind of blocking what I'm looking at. I'm
no, everything's
something.
Fine. Doug,
okay, yeah.
Good.
Yeah, no, it was just getting in my way of seeing this slide, I guess. Never quite sure what's transmitting in the meeting. So what I'm going to do is look at this cross section because it's magnetic with a program called Magneto, and it's operating in 2D mode, which means that cross section sweeps linearly in the direction in and out of the screen. This is a very small transformer, 1.25 inches. Everyone here, I'm sure, deals with things far, far bigger than that, but its size doesn't matter for this purpose. It's more about the generalities. So magnetically, some of the questions that we can look at have to do with like flux linkage and inductance. If we do a calculation that's based on a per turn inductance, then we can simply use the number of turns later to scale it. So you can make all your wire gauge and those kinds of decisions later if you know what's your flux linkages and your inductances per turn. So the self-inductance of a coil is n squared times the per turn inductance for both the primary and secondary, and then the mutual inductance, the coupling between them, is the product of the two. So working per turn is easy. And what you see animating over on the right here is just a summary of a parametric. So the parametrics let me say, okay, I have this proposed transformer, but I'm not committed to the widths in particular here. I don't want to use more steel than I have to. And the basic performance of the device is one of the things to consider. That is, what are the mutual couplings? There's thermal and all that kind of thing that are also affected, obviously, by how much steel you use. But what you see is I've set it up to say, I'm not going to manually change all these widths in my drawing and resolve and get a number and write it down. I'm going to get the program to simply run through as many as I want. And just looking at the dialogues here, you see what we've got is a multitude of parameters defined. At the top moving down, the bottom moving up, those are in sequence. Then for each one of those, the left moving in, the whole coil assembly moving in it, from the left and from the right, those are all individual because they're different steps. But but we can get the program to give us like one of each of those, two of each, 10 of each of those. I can decide how detailed I want to break it down, what kinds of scenarios I want to investigate. So yeah, the parametric consists of those 6 parameters in 2 nested loops. For every position of the kind of sides, we move the bottom up and the top down in 6 different steps. And we then do a query to get some things of interest. And you can see a summary of the table that pops up once the analysis is done here. You can see in this simple case, the inductances per turn within numerical error are all identical. So focusing on one of them is sufficient. I also asked the program to give me the cross-sectional area of the steel core in each of these cases for some extra analysis purposes. So with the 2 independent parameters, I can plot families of curves rather than just one curve. If I had one parameter, I would get something like inductance versus side width. But with the 2, I can choose, depending how I make things primary or secondary, I can get the software to feed back to me what is the inductance as I vary the width for 6 different top and bottom positions, or I could reverse it and get it to give me the curves for what is the effect of varying the top and bottom for different fixed widths. So 6 and 10 or 10 and 6. Either way, I can get the software to provide me a nice summary. And when I know what I'm aiming for, I can say, okay, within the family of inductances that I'm looking for, here's kind of the widths that are giving me that per turn. So again, obviously, if I can spend like 10 minutes setting up all my parameters, setting up all my desired outputs, then hit a run button and let the program just do all that, I can get hundreds of results in a graph to analyze that I can visually kind of pick out what I'm looking for readily, rather than sitting there and manually making all those changes and writing down all the results. So the time-saving benefit should be obvious, but along with that, any kind of automation means that you can have one expert who kind of sets up automations, and anybody with reasonable working knowledge can run them. It also means that all the things to do with tedium, like getting bored and making mistakes because you're simply getting tired of a tedious task, also go away. The software virtually eliminates tedium types of problems. So this is the area that I inquired this is the reason I inquired the area of the core. From the area, I can say, okay, depending how long I make it in the 3rd direction and what steel density I have a certain mass. And so this lets me externally get all the data out of that table and externally do some other calculations. So here in Excel, I've used the area along with a proposed steel to say, okay, if I'm looking at it differently, I say, I don't care about these widths so much as in total, how much steel am I using? How heavy is this thing? How much mass have I used up? So again, you can say, okay, my target was to have 5 within this design. Here is the range of masses that I get with different decisions, and you can look for one that appeals then. So by exporting the data summaries you get out, you can you can find out other things that may be of interest to you as well. So yeah, in summary then, the parametrics are for those things that you can easily set up something very systematic, like varying widths, varying voltages, varying materials. You might have like 20 proposed steels. You could make a parameter that simply runs through them all and gives you the same kind of summary. Anything that you can systematically vary for a design is very amenable to a parametric type of approach. And you're looking to answer very specific questions. Our software is not kind of tell me the best transformer design software. It lets you identify a specific question and address it. So in this case, inductance per turn was the specific question being addressed, but one can readily imagine lots of other questions, again, covering the whole range of heating, electric fields, breakdowns, partial discharge, and so on. One needs to make one's selections about how to do any of those kinds of analyses. So let's look at the B field inside the core. The whole design, of course, is ideally you're working somewhere on the magnetization curve, and you're probably not heavily saturating because you're going to start leaking magnetic field out elsewhere. But if you've got a very weak field, it means you can probably save some money by reducing the amount of steel, at least on the magnetic design aspect of it. Again, a full design, you'll look at thermal effects and so on as well. So by design, these sections, let's call this a width of W here, and here. These are identical, and I've got 2W in the middle. So all the flux that comes up in the middle, that's uniform in the middle, is also uniform along the other lengths. But where it's dividing, where it's going around corners, that's fundamentally going to be a bit different. So in particular, you may look at something like the low field area here. You may say, I wonder if I really even need steel there. It looks like if I got rid of that steel, it wouldn't affect things much. So that very weak flux could easily move in a little bit and it wouldn't change anything. So one may look at some savings by modifying the design by identifying low field areas. But another thing that may happen here is you may look on the inside and say, this is getting dangerously high. This is getting up into where I might actually be saturating and I might be leaking flux out, which I don't want. So you may actually, by looking at simple plots like this for each of your designs, you may identify places to either save or where you've got potential problems. So looking at the corners in particular, I did a variety of plots here just to see how big it gets for the analysis I've got here. And you see the identification, something we do when you do a graph somewhere in a model. We allow you to draw a line of the same color of the graph in the geometry. So the pink line is shown in pink where that comes from in the model here. Your blue line, which barely shows up, is this. Your green line shows up here. And as mentioned, these are virtually identical, virtually uniform. All of these at a very similar value. But then across the middle here, that's where things get interesting. The flux is bending away, so it's a lower field in the middle than what it is along uniform parts of the geometry, but as we come into these corners, as mentioned, it starts to rise and gets very high. And in fact, it probably won't go as high as 3.27 if I put in more time in the analysis and get the nonlinear characteristics correct. What I'll probably find is because the initial analysis says it's that high, what's actually happening is the flux is starting to cut the corner there. And again, if that's undesirable, it most likely is, then you want to work around that. So to work around that, we could set up a parameter. I've not done that here. I want to move on to talk about some other things. But just to show you conceptually, what do you do when a sharp corner is causing the field to get higher than you want? Well, the most obvious thing is you round at the corner. So if I just do a quick manual trial to get a sense of what's going to happen, I put rounding on these two corners where I did my plot. Now my line is a little bit longer because instead of, from here to here, it's going just a little bit further. What you see is that this amount of corner rounding, which is almost as far as I can go with the same coil, proposed coil position, has brought me down so that my maximum field is almost the same value as what I've got on the red, green, and blue sections. So it's done the job of bringing those down, saying that I'm never exceeding some undesirable value, and the low values in the middle are just kind of inherent. Again, if you really wanted to, you could play around with steel in here and so on to try to shape things. So it may be that manually doing that, you get all the information you want. You say, okay, I rounded it, I got what I want, we can easily do that rounding, I'm done. So it might just be manually using the software is all you need. And a lot of what people do is manual. But if you decide that this warrants some actual study, then it may be that you want to study more cases than you really want to manually configure one by one. So your options then for how are you going to automate this are going to be either parametrics or scripting. And this is my branching point then for going off to talk about scripting instead. But with parametrics, you would make a round corner, you would set up a parameter scaling that from an appropriate point and select your various scaling factors and your desired output. Your outputs might be something like the graph that I just made, so that once it's all done, you can make a family of graphs and say, okay, here's all my different rounding radii, here's all my maximum fields. But you can go ahead and set up a parameter like I did for the inductance that would examine this issue. So on a given design, that's one thing. But if this is a very general thing, if you're going to want to do this over and over on multiple designs, or you want to do it in a way that isn't parametric, let's say there's other kinds of rounding you want to look at, and you typically want to look at them. You want to say, well, what about a straight bevel rather than curving it? Those aren't parametric variations. Those are fundamental, trivial, but fundamental changes to the geometry itself, and therefore fundamentally different models. So some things, even though they're systematic, are not possible to do manually. Scripting is the way to automate the material by taking control of it, typically from the outside. Programs might have their own built-in scripting, but typically you would control it from the outside in your choice of environment. And you can make up tools to do a variety of things, including ones that are similar in purpose to parametrics. So I'll just talk about those a little bit here. So yeah, the other thing is I mentioned here, if you have a complex assessment, there may be no simple built-in tool for something like, tell me if there's any area of 1 millimeter squared or greater which has an average field in excess of 1.8 Teslas. It's a very specific, complex assessment that you figured out is important to you. And people often do this for like electric sparking types of troubleshooting and that sort of thing. They're looking at this kind of issue for high fields for saturation purposes. You may also be looking at this kind of thing, saying, if there's some tiny spot where the field gets beyond saturation, so what? What I need to know is there any area greater than this amount which is problematic? So because you can't predefine where that might be, the assessment is fundamentally complex, and there may be no nice parametric way to set it up. But if that kind of assessment is something you do over and over, you can create your own automated tool to do that in any model that you want. So the samples that we provide in particular for how to take control of our program span Excel, and we do most of them this way because everybody has Excel. And for people with basic programming ability, which is all you need, VBA stands for Visual Basic for Applications. So it's a very simple programming environment. Everybody has Excel. Everybody can learn to do this if they have any programming capability. But MATLAB is very popular. Python is becoming very popular. And for people who want to actually make their own desktop app, some very dedicated tool where our software virtually goes into the background. The user doesn't need to know anything about our software because they've defined something that does a job for you without having to see our software, just using it as a background number cruncher to do the finite or boundary elements. C#. C# is kind of your entry point to using a more sophisticated programming environment like Visual Studio. So this first animation, what you're watching is exactly a case of that. It was actually the very first sample I made up. It's in C#, and all it is a simple example of a tool where I've made up a whole bunch of inputs that characterize a generic insulator. And so we have like shed widths, how many sheds there are, and something like how many sheds there are isn't parametric in the sense that we do parametrics, because it's changing the fundamental geometry. So what you're watching there is I just recorded myself using the tool doing a few random things. So you see the tool is designed to give you a whole bunch of inputs and build and solve according to what you set up. So you can create tools like this where, as I say, the user may not even see or need to know anything about electro, because the tool can define all the inputs that you're interested in. It can make graphs and other analyses appear back inside the same design tool. The user doesn't need to know anything about our software to make use of this. So again, you can leverage off of one person who's good with our software combined with another person who's good at programming, or maybe they're even the same person, create a tool and provide it to a whole group who then need to run our software in the background, but don't actually need to know anything about it. So another trivial example, This one being an Excel example, is one that simply takes an insulator and puts it at different places between plates and reports back to me what is the maximum field. And so this one is intended to be a very simple entry point for anybody. If you want to understand how to set up a script in our software, this is how you can do that. You can add in as many more sophistications and inputs and outputs as you want, but this is just to say, okay, watch this. We're going to move this insulator along to 10 different places, tell you the maximum field at each of them, and plot at each of them. And you may have never seen something like a run button appear in your Excel before. Most people don't make use of macros and the like, but anyone with some basic programming ability can learn how to do that quite readily. So just to show the fundamentals, how does this actually work? Here is the code window popped on top of the spreadsheet window. So the code, again, if you program this, will look extremely simple to you. All that the code does is it attaches to our program. So it sets up what's called a handle. I named it Electro here. So it finds our program, IES Integrated Engineering Software. And then any command in this code that starts with electro dot is going to send the rest of it into Electro rather than running it in Excel. So electro dot, create this object, electro dot,
Well, you're muted now, Doug, for some reason.
Okay, sorry
Okay,
about that. How long have
something
I been
happened.
muted?
No, just 2 seconds.
Oh, okay. Okay. Yeah, I don't know what happened. So electrodot sends commands into our program, and here's where we're starting to get into the guts. But as I say, it's a trivial example. It just draws a couple of electrodes, draws an insulator, puts in material, and in this loop, this simple for loop, it'll go through and put the insulator in different positions. That could readily be done with a parametric. So again, this sample is intended to just get you started. And in fact, the way people tend to script, I only ever wrote from scratch one script. It might have even been this one in Excel. Every other sample I made, I take something that pre-exists and just change all the inputs and outputs, and modify the code a bit. But you get all of these kind of fundamental structures in place from one sample, and then you can just edit it. So this kind of thing, it's what I call very linear. It's very much just read everything out of the spreadsheet. In this case, just read this box out of the spreadsheet, go to this sheet, read it, cell value B1, this value of 10, and then loop to 10, perform the same operation using the loop number as appropriate, and then I'm done. Present all my outputs, feed them back in here, and then I'm done. So as far as programming goes, this is very straightforward, very, very linear. But if you have programmers, they can make as sophisticated an application that makes use of our software as they want. And this is really a case of let your imagination do the work for you. Think of what kinds of things you might be able to make use of this for. So again, in summary, both provide a way to automate the program, scripting versus parametrics. Parametrics is a lot faster to set up, but they both work. So scripting simply lets you do far more powerful things, but you need to know that in total you're saving time by doing it. you're not just playing with programming because you like programming. If you're a practical person, you look at something and say, what's the least amount of work in order to get this job done? And it may be manual, it may be parametric, it may be scripting. Okay, so yeah, I've only really barely touched on everything our software can do. That wasn't really my point. My point was just to give an overall sense of these two broad ways of automating the use of software like ours. Hopefully, some of you will have seen some clues of things you could do with our software that would be useful to you. And by all means, contact me or contact our sales if you're interested in looking at the software. I'll take questions now.
All right, thanks very much. We do have some questions. The first question is there a limitation to the size of transformer, either small or large, that this scripting software is applicable to?
No, there's no fundamental limits built into our software and all. And because it's number crunching with units, really, you could say your transformer is miles in size if you wanted to. You could say it's as big as our solar system. The software is simply crunching numbers. So it's a matter of complexity more than physical size. I only show very trivial things that we're actually running. At the beginning, many slides up, I showed some, more complex things like small wires and so on. But even these, like even the transmission tower is not terribly complex. Inside a transformer, you're going to have thousands of bits of paper and foils and it's probably overwhelming in any simulation to say I'm going to put every single detail of any complex transformer in. So it's a question of identifying the complexity of the task you're trying to perform, but things like physical size actually don't mean anything.
Okay, the next question is, I would like to know if your software considers orthotropic material characteristics or will consider it in the near future.
Right. At the moment, we do almost entirely isotropic calculations. I don't want to here get into wordsmithing it too much. For practical purposes, I would say we're isotropic right now. Our material library was configured fundamentally to allow for alternatives, anisotropy, and so on in homogeneous materials. But at the moment, the best way to think about it is to say that everything that I draw has an isotropic property to it. And as I say, potentially I could argue that we go a bit beyond that in some cases, but that's mostly the case.
Okay, we have another question. Have you noticed any advances in grain-oriented steel laminations in the last 20 to 30 years?
That's not really important to us. To me, somebody presents a material property. So we're always being asked, can we get the magnetization curve for a material? And we look around and we've got various ones built in. We mostly end up telling people, the manufacturer should be providing that, and in my opinion, should be providing that per batch if it even matters, actually, because that's why you're buying this material if you're looking for something that's called transformer steel. But people often are working with steels that aren't made for magnetic purposes, and then you're really at a loss to find reliable material properties. But But for me, because I'm working and assisting people with things that they bring to me, we're using this steel, for example. Why they use that particular steel is not really what I do. So I don't really have any opinion on that sort of thing.
Okay.
Yeah, one thing I don't think I quite answered. I got a bit lost in my own words there. The previous question. So will we be doing anisotropy and so on? I mentioned we've built it so that we can. So the answer is yes, we do want to move in that direction. And certainly, like most companies, when sales hinge on things, that affects our priorities a lot. So if somebody really likes our software but says, you know, I need something a bit beyond what you've got, by all means, we may well change our development priorities to make that sale happen.
It's a good idea. Okay, the next question is, I would like to know if LabVIEW can be used for design for scripting.
LabVIEW, I've never touched it myself. So my basic thing would be anything that you can access what's called the Windows COM interface. You can use to control our software. So other ones I've seen used include MathCAD, besides what ones we provide examples for. So from what I know of LabVIEW, there's a very good chance on our website, you can find an example where I used SolidWorks to control our 3D program. I actually have an example where I made a script in SolidWorks and sent the same commands into SolidWorks and into Coulomb, our 3D program, and except our program did an analysis, which then led back and displayed inside SolidWorks. So lots of programs that have their own script abilities, so long as they can access a Windows COM interface, they can control ours. So if LabVIEW lets you do anything like control Excel, it can probably control ours.